We've already explored what happens with rational functions. So a function where we have a polynomial divided by a polynomial as x gets really big. So looking at limits at infinity on rational functions. Well, we can extend those same ideas that we used with rational functions and polynomials to more interesting functions. So functions that might have exponential growth in it, or might have a factorial in it, or might have logarithms in it. So we're going to take those ideas that we use with rational functions, and we're just going to extend that and look at what happens when we have other types of functions in there. So I first want to point out that we defined a rational function as a polynomial divided by a polynomial, so where the numerator and denominator are both polynomials. But we're going to look at other functions now where the numerator and denominator are not necessarily polynomials. They might have other types of functions in them, and the same principles are going to apply. So the basic types of functions that we're going to look at are logarithm functions, polynomial functions, exponential functions, and factorial functions. And each of these types of functions are going to grow at different rates. Kind of like when we had a polynomial, the larger degrees grew faster than the smaller degrees, and we said that those dominated. So we're going to talk about this idea of relative growth. I'm actually going to call it dominance. So we're going to have parts of a function that are going to dominate over others, meaning when x gets big, the dominant part is going to have a greater impact, and the non-dominant parts are going to have an insignificant impact that we can essentially ignore. So these types of functions are listed in the order of how fast they grow. So logarithmic functions, as we plug in bigger and bigger and bigger values of x, are going to grow the slowest. So you can see that as the x values get bigger, it's the lowest of the functions. The polynomial that I used right here is just the line y equals x. That is a polynomial. Even if we had x squared or x cubed or x to the 20th power, that the polynomial is actually going to grow slower than the exponential function in the long run. So even if we had a polynomial that looks like this, maybe an x squared, it's still going to end up below the exponential and the factorial. Then we have exponential functions, and then we have factorials. And remember, factorials, if we have something like 5 factorial, that's 5 times 4 times 3 times 2 times 1. So the factorial function is actually a discrete function. We're going to look at what happens with x values that are just whole numbers. We can look at the the factorial function as a continuous function, but the applications we're going to use it for will be discrete. And we'll get into that more later. So how do we use this idea of dominance? With polynomials, we looked at what dominated the top and what dominated the bottom, and then we evaluated how does that affect the function as a whole. Well, the same idea here. On top, we have a logarithm function, and on the bottom, we have an exponential function. And if you remember, the exponential function is going to dominate the log function because it grows faster than the log function. So because of that, in a function like this is going to be growing faster than this. So both the numerator and the denominator are going to get really big as x gets really big, but the bottom gets bigger so much faster that essentially this is behaving like 1 over infinity. So the bottom is dominating, so the bottom is growing faster. And when we take a number divided by a really big number, we get a really small number, a number close to 0. So if the denominator dominates the numerator and the denominator grows a lot faster, then we take a smaller number divided by a really big number and we get 0. In this example, we not only have the log function on top, but we also have the exponential function on top. So we're going to evaluate what's happening with the numerator and denominator separately first, and then we're going to see what happens as a whole. So in this particular one, just looking at the numerator, the x squared is going to dominate over the natural log. So essentially, as x gets really big, the value of this natural log of x to the 4th is going to be insignificant compared to the value of the x squared. So this function is going to behave like, and I'm going to write that as a limit, it's going to behave like the function x squared over e to the 2x as x gets really big. Well, just looking at this, an exponential function is going to dominate over a polynomial So as we plug in bigger and bigger and bigger values of x, this is going to have a much more significant impact. And just like the last one, this is going to behave like 1 over infinity. So a number over infinity is going to be 0. So again, denominator is growing more quickly than the numerator, then we're going to get a limit of 0. Now, if we look at this going in the other direction, we need to be careful here because x is approaching negative infinity. What happens on top is actually not impacted at all by the fact that x is approaching negative infinity because those are both even functions. So if we plug in a negative number for x here, we're going to get a positive number. So it doesn't matter if we're plugging in 100 or negative 100, x to the fourth is the same thing, x squared is the same thing. The big difference here is what happens with the e to the 2x. So if we plug in e to a negative number, I'm just going to call it e to the negative c for now. If we're plugging in a negative number in the exponential function, remember a negative exponent is the same thing as 1 over e to the c. So if I'm plugging in a large negative number for x, then what's happening is I'm getting 1 divided by a really large number. And so the denominator here is actually approaching 0. As x becomes a really big negative number, e to the x, or e to the 2x in this case, is becoming a really small number. And so even though exponential functions as x gets bigger dominate polynomials, in this case, the exponential function is going to be dominated by the polynomial because the exponential function is getting smaller. So we're actually getting, instead of exponential growth, we're getting exponential decay. So because of that, the numerator is growing faster than the denominator, because in fact the denominator is getting closer to 0, and then we get an infinite limit. Now it is positive infinity because when we take a negative number and we square it, we get a positive, and when we take e to any power, we get a positive. So the dominant parts of the numerator and denominator are both positive, which means it's positive infinity. Had this been x to the third power, if that was x to the third power, a negative to the third power would have been a negative, and then this would have been a negative infinity. Okay, going back to positive infinity, we've got multiple terms in the numerator and denominator here. So first thing we want to do is identify what's going to dominate the numerator and what's going to dominate the denominator. So in the numerator, we have this polynomial here. And when we're dealing with polynomials, we'll always look for the biggest degree if there are multiple terms. And then in the denominator, the factorial is going to dominate. And we could rewrite this as the limit as x approaches infinity of x to the 12th over x factorial. We don't need to rewrite it. We can just look at what happens here and kind of do this a little more informally. So the denominator is dominating the numerator because factorials are the fastest growing of all the functions. And so denominator dominates, we get 0. Now, this problem is going to be interesting because of the square root here. We're going to treat this the same. So this is going to be dominated in the numerator by the 4x to the 6th, but we need to remember it's in a square root. The denominator is going to be dominated by the 3x cubed. So this is essentially going to be the same as the limit as x approaches infinity of 4x to the 6th, but the square root of that, because that's going to dominate the interior of the square root, over 3x cubed. So by doing that, by separating this out, we can say this whole numerator is going to behave like this. And then by doing that, we can actually take the square root. So the square root of 4x to the 6th is going to be 2x cubed. Now, this is going to be more important later, but I want to mention it now. If we were plugging a negative number in for x in this expression, a negative number here to the 6th power is going to be positive, and then a positive to the 3rd power, or the square root of a positive number, is going to be positive. So technically, this is the absolute value of 2x cubed, but since x is approaching positive infinity, it doesn't matter. We're looking at positive values. All right, so the numerator is behaving like 2x cubed, the denominator is behaving like 3x cubed. Now we have the same degree on top and bottom, which means we can just divide those coefficients. So this is going to be 2/3. All right. Now I want to look at a graph of this and start talking about what this means graphically. We've only really been talking about how we evaluate these limits, but from a graphical perspective, as we're plugging in bigger numbers along the x-axis, then the value of the function is approaching 2/3. So what that means is the value of the function here is getting closer and closer. If we plotted the line y equals 2/3, let me try that again. This function is getting closer and closer to that y value. So as we get further to the right, the value of the function is going to get closer to the line y equals 2/3, and we get a horizontal asymptote. So these limits at infinity are representing horizontal asymptotes in these problems. And we'll get into that a little bit more later. Now, I want to talk about what happens with this one as x approaches negative infinity, because this is one we have to be really careful about. As x approaches negative infinity, this is where that absolute value that I talked about up here is going to have a bigger impact. So the numerator is going to be dominated by this, and the denominator is going to be dominated by this. So this is going to be the same thing as, so this is no different than what I did when x was approaching positive infinity. But now we have to consider what happens when we plug negative numbers in for x. So if we plug a negative number in for x here, raising that to the sixth power is going to make that positive, and the square root of a positive number is a positive. By the way, a square root of a negative number is an imaginary number, and so we can see on the graph here where we get imaginary numbers, it doesn't end up giving us values that we would plot here. But in the denominator, we plug in a negative number for x, and we get a negative. So even though we said this was behaving like 2x cubed over 3x cubed, we get a positive divided by a negative, and what's going to happen here is we're going to get negative 2/3 because we have a positive divided by a negative. All right, and if we look at what's happening on the graph going to the left, we had that horizontal asymptote going to the right. Let me try drawing that a little bit better. But we're also going to have a horizontal asymptote going to the left. And so this is the line y equals negative 2/3. And so the value of the function going this way is going to get closer and closer to that y value going to the left. So I want to point out a few features of this graph that are interesting, and some relevant, some not as relevant to this particular topic, but important ideas. So first of all, when we have a limit that of as x approaches positive infinity, that gives us a horizontal asymptote going to the right. If we have a limit as x approaches negative infinity, that gives us a horizontal asymptote going to the left. Horizontal asymptotes and vertical asymptotes are a little bit different. So vertical asymptotes, we're not going to have the function going through vertical asymptotes, and that has something to do with domains of functions, you don't need to know the specifics, but it is possible for a function to go through a horizontal asymptote. So we can see that this function goes through these horizontal asymptotes multiple times, and that's okay. Functions can go through horizontal asymptotes. It happens. All right. What we're looking at is called end behavior. So what happens as x gets really big going to the right, or what happens as x gets really big going to the left. I also want to point out that this graph has some vertical asymptotes. So where the denominator is equal to 0, and we could actually factor this as 3x times x minus, that's not a minus, x minus 1 squared in the denominator. The denominator is equal to 0 at 0 and at x equals 1. So we actually have a vertical asymptote here at x equals 1, and we have a vertical asymptote on the y-axis right here. Okay, so we get vertical asymptotes when the denominator equals 0. We get horizontal asymptotes by evaluating these limits at infinity. I also pointed this out, but where the radicand, the inside of the radical, is negative, and that looks like its values here around 1/2 to about 1. If we plug in numbers in that range, we're going to get negative, the square root of negative numbers, which we can't do in the real plane. So we get a gap in our graph there. That is not an asymptote. It's just where we get complex numbers. One last thing I want to talk about. Oh, there's our asymptotes drawn much more neatly than I did. Um, so I want to talk about why the factorial function grows so much faster than the exponential function, which I think we know that the exponential function grows quickly. Um, so as we plug in larger and larger numbers for x, why does x factorial grow so much faster than e to the x? So what I want to do is consider what happens when we go from plugging in some number, I'll call it n, to plugging in n plus 1. So with the factorial, if we plug in n factorial is the same thing as n times n minus 1 times n minus 2, all the way down to 3 times 2 times 1. If we were to plug in n plus 1, so we go to the next number on the x-axis and plug that in, then what we get is n plus 1 times n minus 1 times n minus 2, and so on. So you'll notice that the n times n minus 1 times n minus 2 all the way down is the same in both of them. So essentially, when we do this, when we move from one number to the next, that's the same thing as multiplying by n plus 1. Okay, so if we think about when we're dealing with really big numbers, so we have a million factorial. That's a million times 999,999 and so on. And then we move to a 1,000,001 factorial. What we're doing is we're multiplying what we had before by 1,000,001. All right, with the e to the x function, if we go from n to n plus 1, well, e to the n is e times e times e n times, and e to the n plus 1 is e times e times e times e times e n plus 1 times. So essentially the difference here is that we have one more e in there. So this is the same thing as multiplying by e. Well, no matter what n is, if we multiply by e, we're multiplying by the numerical value of e, which is about 2.7. So when n is a really big number, with the factorial, increasing it a little bit multiplies it by a really big number. Well, when we're doing the exponential function, increasing n by a little bit multiplies it by e. So as n gets really big, it's growing really fast because we're multiplying it by bigger and bigger and bigger numbers, whereas with the exponential function, as x gets bigger, we're just multiplying it by e over and over. So we're multiplying it by huge numbers here, and we're multiplying it by the same number here. So as x gets really big, this factorial function is going to grow a lot faster than the exponential function. Multiplying by 1,000,001 is going to be much more impactful than multiplying by 2.7.